Now a little bit more on acceleration. So let's take a case where an object crosses the point A going to the right and crosses the point B also going to the right. So this would be V initial and this would be V final, and the time between these two is some delta t. So let's take some examples. So let's say that V initial is 3 meters per second and V final is 5 meters per second. So the object is speeding up. It's getting faster as it goes to the right. Now, in this case, the acceleration is going to be, well, it's always going to be V final minus V initial over the t. Delta t, let's say, is 2 seconds. So the acceleration in this case is going to be 5 minus 3 over 2, which is going to be 2 by 2, so it's 1 meter per second square. That's this case. Now let's suppose that it was going at 5 meters per second here at A, and it's going at 3 meters per second at B, so it's slowing down as it goes to the right. In this case, the acceleration is going to be final minus initial over 2. That's going to be minus 1 meters per second square. So a negative acceleration indicates that it's slowing down, but that's not always the case. In this case, it's negative acceleration indicates slowing down. Let's now assume that the particle was actually going in this direction. So let's do it like this. It's going in this direction, and so that's V initial and that's V final. So it's coming from here and it crosses B and then A. So, and let's assume similar numbers. So here the velocity is minus 3 and minus 5. So it's going at minus 5 meters per second here, and then at minus 3 meters per second here. So it's slowing down. Now the acceleration in this case is going to be final minus initial, and the final is minus 3, and the initial is negative 5. So negative 3 minus negative 5 over 2. Time would always be positive, well, most cases. So it's minus 3 minus plus, so it becomes plus 5 minus 3, so it becomes plus 1 meter per second square. So the acceleration is positive even though it's slowing down. And then lastly, if this is minus 3 and this is minus 5, so it's going from the left towards the right, going from the right towards the left, and it's getting faster. So now the acceleration is going to be final minus initial. Final is minus 5, initial is negative 3 over 2, so it's going to be minus 1 meters per second square. So you could have negative acceleration and it's slowing down. You could have negative acceleration and it's speeding up. The reason is that it's accelerating in this direction. So that's why it's negative. And here it's accelerating, getting faster in this direction, so it's positive. The net result is that if V and A have the same sign, then it's speeding up. So you can see that the velocities are negative in these two cases, and it's speeding up negative acceleration. So velocities and accelerations are both the same sign, so it's speeding up. And if V, and here also it's speeding up because the velocity and acceleration are both positive. Here they're both negative. If V and A are of opposite sign, it doesn't matter which one is positive, which is negative, then it's slowing down. and you can see here the v is positive, a is negative, it's slowing down. Here v is negative, a is positive, slowing down. So when they're opposite sign, it's slowing down. When they're the same sign, it's speeding up. So a negative acceleration does not mean slowing down. You have to see the direction of the velocity also to determine whether it's speeding up or slowing down. Now let's look at how the acceleration and position would vary for different conditions. So we have an xt diagram here, a vt and an at. So this is the acceleration, the velocity, and position. And then we'll repeat things for different conditions. So there are three. We'll look at this vertical column, and then this column. So in the first case, let's assume that the position remains constant. So an object is at the same position, and we would say that, well, x is constant, which means it's not moving. If it's not moving, it means the velocity is 0. And so we will have a curve straight along this, or over here, the velocity remains 0. And being 0 all over means the velocity is not changing, which means if the velocity is not changing, the acceleration also remains 0. Now, if the position is changing in a straight line, so in the same interval of time, it covers the same distance. So in this interval of time, it covers this distance. In this same interval of time, it covers the same distance every time. That means its velocity is constant. And so we will get a straight line over. So because the velocity is constant, so the acceleration remains 0. And now in the third case, let's say that the velocity is continuously increasing in a straight line, which means that in the same interval of time, the velocity increases by the same amount, which means the acceleration is constant. So v is continuously increasing, so the acceleration is constant. Well, it was constant here also. And constant here. So constant 0, but constant here is non-zero. And the position would now go in the form of a quadratic. So this would be a straight line. So we'd say v equals, it's like y equals mx plus b. So this would be v equals some slope, which would be the b would be the initial velocity here, and the slope is going to be the acceleration t, and this would have a quadratic equation. Now we could have variable acceleration also. So if the acceleration itself is not constant, then these curves would be far more complicated, and in this course we will not consider this case. We will only take the case of constant accelerations, which may be 0, positive, or it may be negative, but the acceleration will be constant. Now let's see what would happen if the velocity keeps changing. So you start a car, you go at a certain, you accelerate, then you slow down. So let's take one specific case. So let's take a case where we have a curve like this for the velocity time graph, in which this is a straight line, and then here, so the velocity keeps on increasing, then the velocity becomes constant. That's what happens when you go on a highway. You increase your speed and then you maintain a constant speed. And then let's say you have a small increase in speed, and then again you reach a new speed and you become constant. Okay, this dip is not here. And then you, for some reason, you slow down, and then you have to apply the brake very rapidly, and you stop. Okay, so this is the velocity is 0 means you're stationary here. So let's see how this looks on the acceleration graph. So we will take some lines here to indicate these spaces, and now let's see, you have a positive acceleration, you're increasing your speeds, but it's a straight line, so you have a constant acceleration. Now you're going at a constant speed, so your acceleration is 0. Okay, now here you have a constant acceleration because your speed is increasing, but the slope here is smaller than the slope here, and therefore you have a smaller positive acceleration, which is a straight line, constant. And now you're going at a constant speed, which means your acceleration is again 0. Now your speed is decreasing with a small value, so it means you have a negative acceleration. And now you apply the brakes suddenly, so you have a sharp decrease in speed, a large negative acceleration. And now you're at constant speed, which is 0, so your speed is 0. So your acceleration is 0. So the acceleration curve looks like this. Well, normally when you're driving a car, you wouldn't go like that. There would be some kind of a smoothness over at the edges, but that would mean a variable acceleration, so we look at it like this. The acceleration is simply the slope of this curve.